Hello everyone, this is Myungin Wang, or you can just call me David, and I conducted this research predictive analysis of Seoul bike sharing demand with my mentor, Professor Lanham. So in this project, I developed a linear model to predict the number of Seoul's bike sharing demand. The goal was to identify whether the system would function on a given day by achieving better resource allocation, maintenance planning, and customer service. The prediction is critical for operational efficiency, cost management, and customer satisfaction. And the observation includes 365 days from December 2017 to November 2018. The dataset contains various features including rented bike counts, hour, temperature, humidity, and etc. Python was the main programming language for this project. Libraries such as Pandas, NumPy, Matplotlib, and Seaborn were used for data analysis and visualization purposes. Okay, so three models, multiple linear regression, rich regression, and the lasso, were conducted with 8,760 observations and evaluated using fivefold cross-validation. And finally, model performance was evaluated based on the adjusted R-square value. So, for the business problem, urban mobility plays a crucial role in shaping the livability and sustainability of cities worldwide. As cities continue to grow, the demand for efficient and sustainable transportation solutions increases. Bike sharing systems offer healthier lifestyle and solutions to alleviate traffic congestion and reduce air pollution. According to McKinsey, the future of mobility is evolving rapidly, with micromobility solutions like bike sharing gaining momentum as urban populations seek more convenient and eco-friendly transportation options. Additionally, Gensler highlights the transformative impact of micromobility on cities, emphasizing its potential to enhance urban mobility and redefine urban landscape. So this graph supports the arguments over here that micromobility is increasing. The usage of micromobility is increasing. The purpose of the model is to accurately predict whether the individual used the bike sharing service based on the given features on the dataset where the target variable is rented bike counts. I used the adjusted R-squared value to measure the performance of each model, which measures the percentage of variance in the dependent variable explained by the independent variable. So these are the two research questions. How accurately can we predict the operational status of Seoul's bike sharing system using machine learning? And the second one is, which method is the best model to predict the demand of Seoul's bike sharing service? So my dataset is from the UC Irvine Machine Learning repository, and this chosen dataset contains 8,760 observations with no missing value. Feature engineering. So I removed the column date, which shows the past date record that is not useful in model building. And then encoding. I encoded the categorical variable using one-hot encoding. So for instance, over here, season is the categorical variable. And then handle missing value. Since there are no missing value, I could skip the imputation step. Validations design, I use fivefold cross-validation and I standardized the features. Okay, so when you look at these two charts, that shows the relationship between the independent variable with holidays and an independent variable with temperature. People tend to rent bikes on no holidays, and most of the bikes were rented on days with temperature between 22 and 27 Celsius. And it's possible to infer that they are using shared bikes for commuting during the warm temperature. So this is the overall flow chart of the exploratory data analysis. So after the data processing, I'll move on to the fivefold cross-validation and then regression model building. Lasso, rich regression, multiple linear regression, and I evaluated this regression model based on the adjusted R-squared value, and then model with the high adjusted R-squared value, I infer that model is the best one to predict the demand. So for this predictive analysis, I use multiple linear regression, rich regression, the lasso to predict the outcome. So these are the overall outcomes over here, adjusted R-squared value. And we can see that multiple linear regression and rich regression has the identical adjusted R value. Okay, so this means the model can explain 65.18% of the dependent variable, which is rented bike counts. And either of these method is the best model to predict the number of rented bikes in Seoul. However, since the rich regression includes regularization, it is more robust in various scenarios. So I decided to use rich regression over here. And this is the results that I got after the Python coding. So for the model evaluation, since there are numerous independent variables that affect the target variable, 0.6185 can be considered to be a reliable adjusted R-squared value. The high performance of the rich regression allows the business to make strategy decisions with confidence and reducing uncertainty and improving overall service reliability. So with accurate prediction, Solvay can improve in the following areas, and these are the examples over here: customer service notification, service reliability, and operational efficiency. And this chart shows the relative feature importance over here. This one is functioning day. So as we think intuitively, the demand of the shared bike will increase when the Seoul bike system is functioning, okay? And the second one over here is season winter. So this shows the winter affects the usage of Seoul bike sharing a lot. So people tend to use the bike during the warm weather. As you can see, this bar graph over here in the data section, okay? And so on. So these are all the independent variable. Okay. So in conclusion, accurate prediction for a bike sharing system uses is crucial for efficient resource allocation, improving user satisfaction. The ultimate goal is to promote sustainable urban transportation. So which regression is the best model to predict whether an individual use the bike sharing service in Seoul? And as the dataset does not consider unexpected distributions such as special events and infrastructure changes, the dataset may not include all the possible factors. Thank you.